Hello everyone, in this video we're going to tackle some problems about limits that contain some absolute value signs. And so to begin, let's recall the definition of the absolute value function. What does the absolute value function do? Well, the absolute value of a number x is just going to be x if the input is non-negative. Okay, so if this input happens to be a non-negative number, then you can just drop the absolute value bars, you'll just get back x. However, if the input happens to be a negative number, well then the absolute value function is going to make it positive by multiplying by -1. So for instance, if I had the absolute value of -3, since the input -3 is less than 0, we're going to use the second branch to evaluate this. And so what it says is that we have to do negative times the input, which gives us +3. And so that's how it works. And the way I want you to think about it is x is some input, right? This could take the form of some complicated expression. It could be some linear expression. It could be some quadratic expression. It could be even some trig function. But you want to think of this as your input. If you know that input is positive, then you can just drop the absolute value, right? You can just write 1 plus 2x. If you know that input is negative, well, then you can drop the absolute value, but you have to pick up a negative sign, right? So if for some reason this quantity you know is negative on some domain, you can drop the absolute value by putting this negative sign in front. Okay, good. So now that we have this understanding, let's use this to solve some problems. Okay, so for the first problem, let c be some real number, and they're asking for what values of c does the following limit exist? Does it exist for every single real number c? Does it only exist for positive c, negative c, 0, or is it even more specific than that? Okay, and if you take a look at the limit, you can see there is an absolute value showing up here. And I think the approach here would be to consider some cases. We should consider what happens if c is positive, what happens if c is negative, what happens if c is equal to 0, because this is going to affect the absolute value of x, right? Maybe this is going to help us drop some of these signs. And so let's take a look at this more carefully. For the first case, let's analyze what happens when c happens to be a positive number. If it helps, you can think of this c as being 10 or 5, right, if it helps. And what we're considering is the limit as x approaches some positive number of this expression. Well, think about it. If this is some positive number, as you approach 5 from the right and from the left, all your inputs are also going to be positive. They're going to be like 4.99, 4.999. And from the right hand side, it's going to be like 5.01, 5.001. And so in other words, you're always plugging in a positive number into the absolute value function. And what does the absolute value function do when you give it a positive input? It does nothing. You can just drop the signs. And so that's the trick. That's the trick for this part, is that you can just drop the absolute value signs and you get this. And so now that the absolute value signs are gone, it's pretty straightforward. 1 over x minus 1 over x, they just cancel out, right? You just get 0. And what's the limit of a constant? Is just a constant, right? And so in this case, we see that whenever c is a positive number, the limit exists as a real number. It just happens to be 0. And yeah, you can always try this. Like, I encourage you to try plugging in, for example, 10 or 100. And what you will see is that you will get 1 over 100 minus 1 over the absolute value of 100. But it's a positive number, so you can just drop the signs, right? And so 1 over 100 minus 1 over 100 is equal to 0. And the limit as x approaches 100 is a 0. And the reason, and of course, the reason we can do this is because 100 is in the domain of this function. It's continuous there, so direct substitution works. Okay, so for the next case, let's analyze what happens if c happens to be a negative number, right? We're approaching, the limit point that we're approaching is maybe -5. What happens now? Well, think about it. If we approach -5 from the right or from the left, all the inputs, right? All the inputs x are going to be negative, right? From the right hand side, you're going to have like -4.99. From the left hand side, you're going to have -5.01 and stuff like that. But in either case, the inputs are always going to be negative. And so what happens when you take the absolute value of a negative number? Well, you can drop the signs as long as you multiply by -1 to make that input positive, as we discussed. And so there we go. Now that the absolute value sign is gone, this problem becomes a lot more manageable, right? You can minus becomes a plus, And so this is just 1 over x plus 1 over x, which is 2 over x. And again, remember, c is less than 0. So you can just use direct substitution. It's a point in the domain of this function. You can use direct substitution, and you get 2 over c as the value of this limit, which is also a real number, right? C is some negative number here. It could be like -5. So it's just going to be some real number. And so in this case, we also see that if the limit that we're considering is some negative point, the limit still exists. It's, it depends on the value of c. Finally, let's tackle the last case. What happens when c equals 0, right? What happens as we approach the point 0 from the left and right? Does this limit exist? And this one is interesting because as you approach 0 from the right-hand side, your inputs are going to be positive. And so the absolute value of x can just be dropped, right? If you take the absolute value of a positive number, you can just drop it. However, if you approach 0 from the left-hand side, well, then all your inputs are going to be negative, like negative 0.001. And what happens when you take the absolute value of a negative number? Well, you can drop the absolute value, but you just got to multiply by -1. And so that's why we're going to split this limit up into two cases. For the overall limit to exist, we can consider the right-hand and left-hand limits separately. And so for the right-hand limit, since x is always positive, you can just drop the absolute value sign and you'll just get this. And as we saw, this just simplifies to 0, and the limit of the constant 0 is just 0. For the left-hand limit, our inputs are always going to be negative. And so to drop the absolute value signs, we have to multiply by -1. That's the trick. And as we saw, this simplifies to 2 over x. And now, check this out. If x is approaching 0, right? For example, -0.01, -0.001. Well, then this quantity is going to become very large and negative. And so this is going to approach -infinity. This limit actually doesn't exist. It's -infinity. And so for the overall limit to exist, we need the right hand and the left hand limits to exist and also agree. But in this case, the left hand limit just doesn't exist, right? Let alone agree. And so that's why the overall limit at the point 0 does not exist. Finally, let's just summarize our findings about this problem. What we see is that the limit as x approaches c of this function is equal to 0 if the limit point is positive, right? We saw that if this happens to be any positive number, this just simplifies to 0, and so the limit in that case exists and is just equal to 0. If c happens to be a negative number, like -100, -pi, well, then the limit also exists in that case. It just depends on c. We actually saw that the value is 2 over c. And then the last case was c equals 0, in which case we saw that the limit does not exist. And so to answer the problem, we see that this limit exists for all c that are non-zero, right? For all non-zero c, this limit will exist, and we found the values for that as well right here. For the next problem, we have the limit as x approaches -4 of the absolute value of x plus 4 minus 2x. Well, in this case, the limit point, -4, is actually a part of the domain of this function. And so we can just use direct substitution, and we can see that this limit should evaluate to the absolute value of -4 plus 4 minus 2 times -4. Well, this is just the absolute value of 0, which is a 0, and this part is +8. And so the final answer would be +8. The final answer would be +8. But let me just show you, I guess, the longer way to also solve this problem, just so you sort of get some intuition of how to deal with these absolute values if this happened to be indeterminate. We'll look at that in more examples later on, but I think this is a nice toy example to see what's going on. And in order to do it the long way, we have to understand when is the quantity x plus 4 positive, when is the quantity x plus 4 negative, right? We want to find this transition point because, that's going to help us drop the absolute value signs. And so just by definition, the absolute value of x plus 4 is just going to be x plus 4 if this number happens to be non-negative, right? And it's going to be negative x plus 4 if this number, this input right here that you see, happens to be negative. And so you can simplify this a little bit You can distribute the minus signs here, minus x minus 4, and you can simplify these conditions. And what we see is that the transition point is minus 4, right? Every single time you're to the right of minus 4, then this quantity is going to be positive. If you're to the left of minus 4, then yeah, this quantity is going to be negative. And so this is going to help us drop the absolute value sign. Because what you see in this example is that we're taking the limit at the transition point itself. And so to evaluate this limit, you have to consider the left hand and the right hand limit separately, as that will help you drop the absolute value signs. So let's take a quick look at how to do that. Okay, so let's begin with looking at the right hand limit. Well, as you approach negative 4 from the right hand side, all of your inputs are bigger than negative 4. All of your inputs are bigger than negative 4. Well, if that's the case, then we know that the absolute value of x plus 4 just simplifies to x plus 4. You can drop the absolute value signs because this input is positive. And so that's what we're going to do. We're going to replace the absolute value signs with just x plus 4, because as you approach from the right of negative 4, it's just positive. And so now this is a very simple limit to solve. You can subtract, you can do x minus 2x, you get minus x plus 4, and you use direct substitution, you get 8. And for the left-hand limit, very similar idea, but this time we're approaching negative 4 from the left-hand side. So our inputs are smaller than negative 4, right? Smaller than negative 4. For example, like negative 4.01. And so when you plug inputs smaller than negative 4, this number is going to be negative. And so in order to drop the absolute values, we have to pick up a negative sign, right? We have to do negative x plus 4. And that's exactly what we see in the work that we did above as well. Whenever the input is less than negative 4, this quantity is negative. It simplifies to this if you want to drop the absolute value sign. And so yes, now that we have this, you can collect like terms and you get this. You can use direct substitution, you get 8 again. Okay, and so this just confirms the result that we already saw above with direct substitution, that the value of the limit exists, right? The left hand and the right hand limits both exist, they both agree. And so that means the overall limit is defined and it's equal to 8. And again, this one is a little bit overkill for this problem. The limit point is in the domain of this function, which is a continuous function. You just plug it in, you will get 8, no problem. But the point is to show you how to deal with these absolute value signs, how to drop them, right? And yeah, simplify your answer. And it's by considering these left hand and right hand limits separately, and to see if the thing inside the absolute value is positive or negative. If it's positive, you can just drop the signs. If you know that's going to be negative on your domain, then you can drop it, but you have to multiply by negative 1. That's the idea. Okay, so now let's take a look at the next example, which is the limit as x approaches negative 2 of 2 minus absolute value of x divided by 2 plus x. And so I always recommend that you try the direct substitution approach first. Maybe the limit point happens to be in the domain of the function that you're looking at, in which case direct substitution will work. However, if you try it in this problem, we will see that we get 0 on the bottom and we also get 0 on the top. So it's indeterminate. So it doesn't work in this case, direct substitution. And so we will have to convert this into a different form in order to be able to check if the limit exists or if it doesn't exist. And again, the idea is to think about your inputs. You can see in this case that the inputs are very close to negative 2, right? The inputs are going to be approaching negative 2 from the right and from the left. In either case, your inputs are always going to be negative. So what happens when you take the absolute value of a negative number? You can drop the absolute value as long as you replace it with negative x, right? You multiply by negative 1 to make it positive. And so that's going to be the approach. So let's try that and see how this simplifies. Okay, and so as I was just saying, what we're doing is we're considering the limit as x approaches negative 2, right? Well, x is going to be very, very close to negative 2. It's going to be something like negative 1.99 or negative 2.01. In either case, it's a negative input being fed into the absolute value function. And so, yes, in this case, you can just replace the absolute value function with minus x. That's the trick. And so now you can see that minus x becomes positive x. And what's nice about this is that it fully cancels out and you just get 1. And so what's the limit of the constant 1? It's just going to be 1. And so that's how you solve this problem. It's just going to be 1. And the last thing I want to mention is, in case you're wondering how come we didn't consider the left hand and the right hand limit separately, well, you could do that but it's going to amount to the exact same work, because in either case, whether you approach from the left or you approach from the right, the inputs are negative, right? And so this quantity is always going to reduce to negative x. So in case you were wondering, you just have to write it out once in this case. Okay, and so now let's take a look at the final problem of this video, which is the limit as x approaches 0.5 from the left-hand side of 2x minus 1 divided by an absolute value we have 2x cubed minus x squared. And so in this case, we're only approaching 0.5 from the left-hand side. And so yeah, we have to think about that. If we're only approaching 0.5 from the left-hand side, our inputs are like 0.49 and 0.499. And if we factor this quantity over here, we can sort of see what's positive, what's negative, and that might help us remove the absolute value signs and evaluate the limit. And so let's analyze this more carefully now. Okay, so the first thing that we're going to do is we're going to factor the bottom. We can take out an x squared term, and so we'll be left with x squared and then in brackets 2x minus 1. And so now you should remember this very basic property about absolute value, which is that the absolute value of a product is the product of the individual absolute values. And so this lets me rewrite this as the absolute value of x squared times the absolute value of 2x minus 1. And so now it's a little bit easier to understand, is this thing always positive? Is it always negative? Is this thing always positive? Is it always negative on the domain that we're considering? And that's going to help us remove the absolute values, right? The whole goal is to remove the absolute value signs. Now the first term over here, the absolute value of x squared, that's very easy because x squared is greater than or equal to 0 for any real number. For any real number, this is going to be true. And so the absolute value in this case is redundant. You can just drop it here, no problem. And now let's take a look at 2x minus 1. Well, on our domain, we're approaching 0.5 from the left-hand side. So our inputs are like 0.49, 0.499. When these are the inputs, you can try on your calculator, but you'll see that this quantity will always be negative. And so if I want to drop the absolute value, I will have to write negative 2x minus 1. So that's the trick. To be a little bit more formal, we can actually consider the definition of the absolute value of 2x minus 1 on the side here. And so if this input happens to be positive, we just output the input by definition of absolute value. And if this input happens to be negative, well, then we output the negative of the input. And then you can simplify this a little bit. You can simplify the conditions. For instance, when x is greater than or equal to 1/2, you just get the original input. When x is less than 1/2, well, then you can distribute the minus sign here. You get 1 minus 2x. And so in this case, we are always to the left of 1/2. We're in the bottom case. And so like I was saying, it's always negative, right? It's always negative. And yeah, we have to, if you want to drop the absolute value signs, we have to multiply by -1. And so now let's see how this simplifies. Okay, so let's take a look at what we have now. For the x squared term, I have dropped the absolute value signs because x squared is always greater than or equal to 0 for any real number. So we can just drop the absolute values. And as we discussed, the quantity 2x minus 1 is actually negative on this domain, right? As we approach 1/2 from the left-hand side. And so in order to drop the absolute value signs, we have to just multiply by -1 and we can drop them. And so there we go. Now what happens is that if we just rewrite this a little bit, you'll see that the negative sign is over here. And we have the same factor on the top and bottom. So we can just cancel that out. And so we're left with 1 over -x squared. And so now the limit point is in the domain of this function. You can use direct substitution to evaluate it. And the answer that you get is -4. And that completes this problem as well. Okay, great. So that brings us to the end of today's video. I hope you found this video helpful. I hope this video gives you more confidence when you're evaluating limits involving absolute value signs. But if I was to summarize, the main idea is you really want to analyze how the inputs are behaving as you get to your limit point, right? As you approach -4, is the quantity inside the absolute value function positive? Is it always negative? Because if you can determine that, you can actually just drop the absolute value signs, right? The whole goal is you want to be able to drop these absolute value signs. And always remember that if the point is in the domain of the function, you might not have to do a lot of work. You can just plug it in and you're good to go. You can use direct substitution. But most of the time, it's going to be in some kind of indeterminate form. And so that's where you want to analyze maybe the left hand and the right hand limits separately, or yeah, you want to reason about what's happening as your inputs approach this limit, as this limit point. Or is the quantity inside the absolute value sign always positive, negative? Because that's what's going to help you drop these absolute value signs and get a more simplified expression. And that brings us to the end of today's video. If you have any questions, any comments, any concerns, please feel free to leave them down in the comments below. I'll be more than happy to respond and get back to you. And best of luck in your studies.